My name is Jeff. I am the president of the San Diego Marine Aquarium Society. We're the organization that's hosting the event this year. So I just wanted to thank you guys for coming out. We really appreciate it. You guys having a good time so far? That's very good to hear. I really am happy that you guys are enjoying yourselves. It is my pleasure to introduce our next speaker, Dana Riddle.
Jeff, stick around for just a moment. Would everybody give Jeff and the crew that put this conference together a big hand? They really deserve it. The speakers are just the cattle. Okay, we got a couple of people coming. I'm sorry?
We're only quoting you on that.
Got a couple of people coming in. Let's let them get seated. Okay, today we're going to talk about how we as masters of the little reef aquariums we have, how we can manipulate different parameters in the aquarium and make the corals grow faster, or if you want to slow it down, I think I've got some information for you there too. Before we share some of the coral secrets, I want to share a couple of secrets with you. Number one, I am a terrified public speaker. The first 5 minutes, I absolutely tremble. I am shaking. I don't know if you can tell it or not, but I've done like 60 presentations and I'm still terrified the first 5 minutes. So we're going to talk about how to turbocharge photosynthesis, and the parameters we're going to discuss are light, flow, and alkalinity. And when you get all those right, you're going to be able to boost the rate of photosynthesis in your corals or plants or anemones or clams or what have you. Now, these experiments took about a year to complete. Normally, the invitation to do a presentation at a MACNA comes about a year out. And that gives me time to formulate a hypothesis and then go into my little laboratory and perform these experiments. So I think I've got something of interest for you. Now, in order to do this, you got to have, I think this is about $15,000 worth of equipment. We're going to use a quantum meter, which is, make sure I've got this thing pointed the right way. There we go. The quantum meter. I also used a pH and temperature data logger, a chlorophyll meter, a PAM fluorometer, which is a photosynthesis meter, and then a electronic water velocity meter. And we put all this together, and this was one of the preliminary setups. I took a picture. As you can see, I used a little coral plug there, and this is the fluorometer and the water motion probe, and this was the light sensor. This is not the one I used. I used the Lycor, which is a little better for this purpose. So I put all this stuff together, and of course things don't work out right. Batteries die, and you know, I may have problems calibrating the equipment. So there were times I would go in the lab at like 7:30 in the morning and wouldn't actually get started till maybe 10 o'clock or 11 because I had some problems to deal with. So I would take photographs of corals in the meantime to while I was waiting things to equalize or calibrate or whatever, and it tended to relax me a little bit. Now, I did take a look at this picture, and this coral right here was not being very cooperative. In fact, they were being very uncooperative. There's another one right there. So let's talk about light and photosynthesis. Who believes that corals can use an unlimited amount of light, that it doesn't matter how much you give them, more is better? Does anybody believe that? No? Good, good. Does anybody have a par meter in here? Okay, good. We've got a few people. And I'll try to explain why it's important to have one of those. Why do we need to measure light? Well, zooxanthellae, the symbiotic algae that live in the coral or anemone or clam tissues, they require the proper amount of light, and they contain chlorophyll. And as you can see here, most of the zooxanthellae are in the coral polyps or immediately around the polyp, and the reason for that is when the coral eats, that it creates fertilizer, which these zooxanthellae use. Now, the coral I chose to use was a Parietes lobata, and if you've ever been to Hawaii, you know that these are very, very common in the tide pools. And that's the green guy here. And these are not very large in this tide pool. I wanted to do the work here because they are going to get an almost, well, they'll get as much light as you can possibly get in Hawaii. We're on the southernmost island. This tide pool never gets more than just a few inches deep. And this is one end of the tide pool. And as you can see here, it's kind of difficult to tell. This is an artificial dam on one side of the tide pool, and the water splashes in from the other side, and it pours over this dam into the ocean. And I've got a video here, and let me try to get that to work here. See if we can do that. Well, there's some sound with it. We don't have that. But as you can see, the water comes through a blowhole and comes in on the west side of the tide pool, and it proceeds and sloshes back into the ocean. So this tide pool can be 5 or 6 feet above sea level at low tide. So that's the reason that it never gets very deep. And as I say, these corals are going to get probably the most amount of light that you possibly can in Hawaii. Now, to judge photosynthesis, I had to use a PAM fluorometer, and this works on the principle of fluorescence and chlorophyll. And chlorophyll and, the fluorescence and photosynthesis are competing processes. When the fluorescence is high, that means that photosynthesis is low and vice versa. And as you can see here, this is under a black light, and you can see the chlorophyll is concentrated around the polyps and on the tip. And you can still see just a little bit of that fluorescence under the white light. And here, this is Chaetomorpha, and it also has that red fluorescence. And if anybody has any questions while I'm talking, if I haven't made myself clear and you have a question, if you want to stop me and ask me, if you have the question, somebody else probably has the same one. So wave at me, shout, throw something at me, and get my attention, and I'll try to answer that. So is everybody with me so far? Everybody good? Okay. Now, if we take that fluorometer and we measure PAR with a quantum meter, we can determine the rate of photosynthesis through that coral, and we can determine how much light it actually needs. Now, I collect PAR meters, and this is the professional lab grade meter that I have. It's about $2,500. It's a data logger with a 2 pi cosine corrected underwater probe here. And this is more of a hobby grade here. These are getting much better. Apogee Instruments just came out with a new sensor that is very close to the much more expensive Lycor. And there are some that you can plug into a USB port on your computer. And the price on these is, less than a couple $100. So I'll try to show you why you need to measure the light in your aquarium. And if you can't afford one of these and you're a member of the club, maybe you can get the club to buy one for you, and so the members can use. So when we put these instruments together, at the bottom here you can see the amount of light. And here's the rate of photosynthesis. And as you can see, at 0 light, we have no photosynthesis. And as we increase the light level, the rate of photosynthesis goes up. And it gets to a point where it levels out. And let me show you here. This is how the scientists figure out how much light they actually need. They follow this trend line up where it intersects with the maximum rate of photosynthesis, and then they draw the light downward. And this coral that came out of that tide pool, it's just a couple of inches deep, which gets an incredible amount of light during the day. It actually maxes out on photosynthesis at a par level of just a little bit over 100. It's maybe 115 or so. This was another part of the same coral. I chipped off a small piece of it. There was a shaded part of it. And look at what happens when your light level gets too high. Photosynthesis actually starts to shut down. And let's go back to that one. The rate of photosynthesis actually starts to go down. So if you've got an aquarium and you feel like giving the coral more light is going to help it, if you'll look here at 350 micromole, which is not all that uncommon in aquariums, you have the same rate of photosynthesis at about 75 micromole as you do at about 350. So you can definitely overlight corals in an aquarium. And when it goes into photo inhibition, that means that the coral is probably not going to grow as fast. And it's possible that you can damage some of the zooxanthellae within the coral tissue, and that the zooxanthellae will expend a lot of their energy in repair. So let's look at what this coral gets in the tide pool. I did this several years ago. Now remember, this coral, it was going to reach the maximum rate of photosynthesis at, like about here. So look, before 9 o'clock, that coral is going to be photosynthesizing at a maximum rate, and it doesn't get back to that point till sometime about 5 o'clock in the afternoon. The rest of the day, that coral is going to go into shutdown as far as photosynthesis. That rate of photosynthesis is really, really going to slow down. So, as I say, it's entirely possible to overlight these animals. Generally, if you keep the par level at 100, maybe 200, you're going to be doing pretty good. If you want to generate color and you're looking for higher par levels, you can get the color, but your coral growth rate is probably going to go down. Now, this is a Porites in deeper water, and you can see how big they get. So it makes you realize that the corals in that tide pool really are stunted in growth, because these things can get huge. And I've seen photographs of larger ones. But I mean, these animals can get massive, and these are some of the longest lived animals in nature. These corals can live for thousands of years. As I was doing the experiments, I realized that I was seeing some things that I couldn't explain, and this was originally not part of the experiment. I started to look at the chlorophyll content of the corals, and we can do that with a meter. It's a point and shoot. It's easy to use. It's not very cheap, though. I think this instrument was about $3,000. So I've really got to work to make this thing pay for itself. So this is small Porites I chipped out of the tide pool. And as you can see here at the bottom, we've got the top part of the coral, the exposed side, which was the part that tended to receive a fair amount of sunlight. And then there was a shaded side too. Can you tell which one is bleached? Anybody got any idea? The top? Yeah. What about the other two? Can you tell any difference between those? Can you? Maybe my eyes are bad. I really can't tell that much difference between those two. It still looks pretty brown. As you can see here on the top, we've got a little bit of pink coloration, and this coral is actually so damaged that it's losing tissue and some algae is starting to grow on it. But on the exposed and shaded side, you know, we're not seeing that. It still looks kind of brown. So here are some readings with a chlorophyll meter. On the top, this meter goes down to about 40 milligrams per square meter. And once it goes lower than that, it starts to get a little bit flaky. But as you can see here on the very top, the meter could not even read the amount of chlorophyll that was in the zooxanthellae. And then there was a reading here just on the side here, part of the shaded side of the coral. And as you can see, that chlorophyll level jumped way up. On the exposed side, we had a 0 there. That was on that little knot. And then 21. And then we flip it over to the shaded side, and you can see the zooxanthellae chlorophyll content goes way up. So we got like a 236 there. So that's one thing I should have known, but it was reinforced and when I was doing these experiments that the chlorophyll level is not consistent around the coral. And if you happen to take this coral and put the shaded side in strong light, you're really, really going to damage that coral. So that's one reason that orientation is so important when you move these corals around. If you move them, try to make sure that they still have the orientation toward the light. Alkalinity and photosynthesis. This was the major thrust of the experiment. I wanted to see how alkalinity would impact the rate of photosynthesis, or if it would. Of course, I didn't know the answer when I started this, and I designed the experiment, and I go through 2 panic modes. The first panic mode is about 3 or 4 months into the experiments, and I'm not sure things are going to work out. And then the second panic mode is when I get up here on stage. So I think I'm past that, though. So you're wondering how alkalinity might play a part in photosynthesis. And as we learned in school years ago, carbon dioxide is used in photosynthesis. Well, in aquatic environments, and especially in corals where you've got a mix of animal and zooxanthellae in the same tissue, the respired carbon dioxide will not meet the requirement for photosynthesis. So therefore, bicarbonate, which we'll refer to as alkalinity, it can be used as the carbon source. And of course, that carbon goes for growth and making the simple sugars that the coral can use. So this was the hypothesis. The bicarbonate content acting as the carbon source can influence the rate of photosynthesis. And again, in terrestrial plants, CO2 is the carbon source. In aquatic environments, some of the respired CO2 can be used, but it's many times it's going to be the bicarbonate that is actually used. So what happens is there's an enzyme called carbonic anhydrase, and that converts the bicarbonate over to carbon dioxide and water. And of course, at the pHs that we normally see in the ocean, the red line here, this is the bicarbonate content of seawater. So as you can see at the pHs that we see in aquariums, bicarbonate is by far the predominant source. So there's a lot of bicarbonate there for the corals or zooxanthellae to use. Now, this is how it works. And this is known for one coral, but possibly not all, that this carbonic anhydrase can be external, and what happens is the bicarbonate doesn't want to pass through the cell membrane, so it's converted by an external anhydrase to carbon dioxide. Once it goes inside, it's converted back to the bicarbonate so it doesn't diffuse back out of the cell wall. Then it's transported by a bicarbonate active transport. Then it's converted back to CO2, which is used by the zooxanthellae. So we think corals are being a very, very simple animal. They're really not. One thing, I read a paper that suggested that some corals do not have this external carbonic anhydrase. So they suggested that if a coral does not have this, it's going to be a slow grower in nature. So that was suggested. They were going to go back and work on that and see if it's true. But in any case, it takes a lot of processes for this bicarbonate to get into the zooxanthellae and be used as that carbon source. Is everybody with me so far? Is everybody good on that? Have I explained it? Okay, good. So, experiments procedure, I used natural seawater. I walked across the street about 150 feet from the Pacific. I toted like 55 gallons of salt water back up to the house, which completely wore me out. And I took a nap for like 2 days after I did it. I spiked the water with ammonium hydroxide in order to destroy the alkalinity. The nitrification process will naturally destroy the alkalinity. So I got the alkalinity down to 53 milligrams, which is about a little less than 3 DKH, or if you prefer milliequivalents per liter, is that. So what this would simulate is if you were the worst reef aquarium keeper in the world, this is what your water would probably look like. Then I took I was able to calculate the amount of bicarbonate that I could add to the water, and I raised the level up to a normal level, and then I really raised it up to like 12 DKH. And I didn't show it on this slide. There was an intermediate there that I used, and we'll see that in just a minute, but we'll see how alkalinity affects photosynthesis. So there we go. Here at the bottom, we've got the alkalinity levels, and here's the rate of photosynthesis. So as you can see, at 53 milligrams as calcium carbonate alkalinity, the photosynthesis is like 62. Here at the normal, this is pretty close to the normal level. It jumps up to about 75. Then I raised it a little more to 155. And then at 215, you can see we got a substantial jump here. So I did these experiments 3 or 4 times, and I got the same result every time. So just simply by increasing your alkalinity level, you can turbocharge photosynthesis and increase it by about 40%. Yes, sir?
So what are these numbers on the bottom mean and the numbers that we're used to seeing?
These numbers?
Yeah.
Yeah, these are the alkalinity in milligrams per liter. So,
Is that the same as ppm?
Yes, milligram per liter and ppm are roughly the same. There's a little bit of difference because of the seawater content, but yeah, roughly the same. So this, if you use DKH, this is about 12, this is about 7, and this was about 3 DKH. Is that what you use when you measure alkalinity? You go by the DKH? So, okay. So, yeah, the question is what these numbers mean, and did that answer your question? Are we good? Okay. Is everybody still with me? Okay. So, you can substantially increase photosynthesis simply by raising your alkalinity level. And there may be a danger in that. We'll talk about that in just a minute before we get out of here. Water motion in photosynthesis. This was part of the experimental design. I wanted to see if water motion would influence photosynthesis. And obstacle number one for nutrients getting inside the coral is you've got something that's called the boundary layer. And this boundary layer is a layer of stagnant water around the coral. And when your water motion is low, this boundary layer gets thick. And that hampers diffusion of nutrients in or out of the coral. When the water motion is high, that boundary layer can get very, very thin. So your nutrient transport across that boundary layer is going to be much, much higher. And as we discussed, the obstacle number two is getting that carbon dioxide level, the bicarbonate through into the coral, and that goes back to the enzyme that we talked about. But in any case, we wanted to see if water motion would overcome that thick boundary layer, or if we got it to thin out, if photosynthesis would go up. So to do this, we used this is the electronic water meter. It's a great instrument. They're very, very expensive. I've had this one for years, and it's worked like a champ. I think I've had this one for like 20 years. And then we use the fluorometer, which will measure the rate of photosynthesis. So I would take, I had a small pump, which I could turn the flow rate up and down and adjust it, measure it with a meter, and then look at the rate of photosynthesis. And as you can see, when I increase the water motion from about 2 inches per second up to just a little bit under 4 inches per second, we got at the high alkalinity level, we got an increase of almost 30% in photosynthesis. So there's definitely a relation between your alkalinity and the water motion. So I think you can start to see a trend here. If you want your corals to grow fast, you can increase your alkalinity and increase your water motion. If you don't want them to grow fast, don't monitor your alkalinity and turn your pumps off every once in a while. And if you don't kill your corals, they won't grow very fast. There again, this is just a relationship, the rate of photosynthesis between the water motion. This top one is the high water motion, and this is the low water motion at various alkalinity concentrations. But I did look at those separately, and water motion will definitely influence. This is just another way of showing it. I thought this might be a little easier. So if you increase your alkalinity from 53 milligrams to 215 milligrams and increase your flow, your rate of photosynthesis will go way, way up. So, conclusions. I don't want to read to you, you're all adults, so I just zoom right through this. Light, water motion, and carbon uptake are closely linked. The big thing is corals don't require a whole lot of light. If you don't have a parimeter, try to get one or borrow one, because it really is possible to overlight your aquarium. Alkalinity can influence the rate of photosynthesis by as much as 50%. Water motion can influence the rate of photosynthesis. So, if you can, measure light intensity, measure your alkalinity on a regular basis. Water motion is very expensive to measure, so if your sand bed isn't moving around, you probably don't have enough water motion. My experiment, the water motion was about 4 inches per second. That's all I could get out of the little pump I had. In the ocean, off the coast of Kailua Kona in Hawaii, the water motion is about 6 to 8 inches per second, and that's on a calm day. During storms, it's too dangerous to get out in the water. I have no idea what it is. You can measure alkalinity. You can measure light intensity. And if you're only measuring one of those, the odds are stacked against you for success with corals. I wanted to talk very briefly about high alkalinity levels and the possible danger. And if you've been keeping Acropora, you've probably seen or heard of the alkalinity tip burn. If you'll look here, the chlorophyll is concentrated in areas almost exactly where the coral is getting the most light, and it has the most chlorophyll, which means it's got the most zooxanthellae. I think these are linked. When I get back to the mainland, I want to look at this a lot closer. But it is possible that it could be a bad combination, and especially in corals that have very thin tissue layers like the Acropora and Stylopora and all those. With the Porites, I don't think it's going to happen. They've got just massive amounts of tissue, so I didn't see that in these experiments. And I have a chloral bleaching experiment going on. I was hoping to have that completed by the time I came up here, and vacation really crept up on me, so when I get back, I'm going to take a look at that. And I'm going to say farewell to you with a beautiful Hawaiian sunset. I'm going to trade this to look at the neighbors' trash cans in Atlanta in just a few months. I'm going to get back and have a real reef tank. And, oh yeah, I'm going to be close to family too. So I've got my priorities straight. Okay, that's what I've got for you.